All right. Happy warm afternoon to everybody, and welcome to today's session, data science class, where we will continue different aspects of the multimedia, the data within the context of data science applications. We will look at uh, after the Tuesday's introduction, we will be looking at some challenges and opportunities here, and as well as some application areas. We will be a bit more practical and technical also. And there's going to be some projects that I'd like to discuss towards the end of the session today. That should give you some opportunity to put some of these concepts that we're discussing into practical use, whether for the purposes of this class or it may also be relevant in your graduate research work. Any questions, comments, or suggestions regarding what we did on Tuesday? Let me know. Otherwise, we will be looking at some of the challenges and opportunities in this area. We did make an introduction to what the concept of multimedia is, right? So when typically more than two media types are involved in any system, and we did that from a more database-centric approach last time. But whether it's the data management, data storage, the data networking system, or retrieval, querying mechanisms, etc. Multimedia typically refers to the presence of multiple types of media in that system or context. And we know different types. So some of these different media types also overlap with each other. So, for example, many of the video features, processing techniques, challenges, etc., will also apply to images and audio and even text for obvious reasons, because video can be basically a combination of these media types with its own features and challenges as well. So there will be some overlap between the different media types. Graphics and images are similar in many ways, but they can be different. So each media type comes with its own ways or requirements to be represented in a data-centric application, database or otherwise. And then the combinations will also provide both challenges and opportunities. So if you're relying on, for example, multiple modalities for a person recognition, you may recognize a person in a video clip from their voice, from their face features using image features, and even from video features from their gait and the way they walk or move, for example. So all three modalities may present different ways, different sources of information, and combining them itself, the combination may also potentially provide the opportunity or the advantage. So multimedia is not just the presence of these different modalities. Very often it refers to the fact that you can handle and process multiple dimensions, multiple media types, multiple modalities in some cases, for a common purpose, whether it's data indexing, retrieval, compression, or other areas. For example, video compression, efficient representation of video will involve compression in both spatial and temporal dimensions, in other words, in terms of your image frames, as well as the sequences of images will be compressed. And this is the case even for the audio track. So you have basically a combination of multiple modalities, even for a relatively straightforward task like compression or encoding of uh, video data. So the content-based indexing and analysis and representation, and also retrieval of multimedia data is obviously one of the key challenges. So we will look at some of these technical aspects, how the major approaches can be on what feature set and what indexing mechanisms they can basically rely on. And I mention a few applications, and we will also tie that to some of the project ideas, and we will get into some of those technical details next week in both image, video, and some of the audio aspects as we discuss some of the technical approaches in more detail. So we know what media is, what multimedia is, and more than two media types will need to be involved in any system when you call it multimedia. But it's not, as we briefly discussed, it's not just the combination of presence of these media types, but often simultaneous processing and or co-processing, and sometimes cross-processing. So you can basically take advantage and in some cases address the challenges of the presence of multiple media types. So just having audio and video, visual tracks in a video data doesn't make just, that video data itself multimedia. Obviously, that's just an enriched media type in itself. So many systems address these challenges and take advantage of the opportunities by representing media through some indexing mechanisms and with the help of some kind of a feature set. So these will typically involve digitization of the objects. So multimedia data in its natural form, interestingly, is not digital alphanumeric data, can better be represented in a more natural way in digital formats, things like character sets, ASCII character set, Unicode character set. Obviously, numbers and binary logic fits better the idea of the traditional alphanumeric data. The multimedia data by nature, in most cases, like the audio and then visual data, and other sensory data as well, like temperature data, etc., is not naturally in digital form. So digitization and in the process, the capturing of the relevant features will be an important part of the representation of this media. For both exchanging the digitized data, for storing, representing along different feature dimensions, and ultimately being able to present the data to the user in its most useful form, and by preserving the perceptual features or perceptual qualities of the media. So these will be different dimensions of dealing with multimedia data from the start, the initial stages of digitization, sampling, etc., turning your otherwise natural multimedia data form into digital format, basically sequences of zeros and ones, and in the process, preserving the important features, especially the semantic features, being able to store and transmit them in an efficient and effective way, and making them both available to retrieval database mechanisms, etc., like we discussed last time, and also presentable in according to the user requirements and preferences. So the term multimedia information system is in a broader sense than some of the database specific aspects that we discussed last time, involves several technologies uh, and uh, and basically combines them and in many cases requires them also. Digital signal processing and in particular image processing obviously is a very important part. So signal processing is a more general term that may involve just general purpose signals, audio signals, an important part. Uh, Obviously, you can consider video also as a combination of audio and visual signals or images. So the reason these signal processing or image or other uh, areas like audio and or video processing is important is because the data that you're dealing with in its original form as well as in its final presentation is not the digital by nature. So the sound is actually, or the audio as we perceive and often produce it, is an analog signal, right? What do we mean by this? It's a continuous real world uh, uh, phenomenon that's basically vibration uh, of objects or of air in its final form. So in order to perceive audio signals, we need to present it in that natural form, and very often the data is captured in its original form as an analog signal, and then you need to convert this to electrical signals for initially in analog format, meaning just some voltage level that varies in time. And obviously, you need to digitize that by capturing the samples at certain intervals, etc. So signal processing, image processing, etc., will be heavily involved in both capturing the initial creation of multimedia data and also in the final reproduction or presentation of the data. So when you, uh, for example, just click on a YouTube video, right, these days, or any audio clip, you play it back, and the way you hear or view that is in its final format. So you need to produce these light signals so your eyes can perceive the image that you're creating on a screen or a similar device. And also you need to recreate or reproduce the audio signal from the digitized format. So this is important on both our input and uh, output end of the process. So computer graphics obviously deals with more synthetic data as opposed to digital video technologies that allow you to capture real world data uh, and digitize it or vice versa. Computer graphics completes that with more synthesized data in terms of the computer graphics, computer generated imagery, videos, animations, etc., as well as maybe some domain specific data like GIS data uh, or computer aided design software, etc. So those technologies will also be involved in both creation, processing, storage, and presentation of multimedia in an information system. So we talked about some database aspects involved in multimedia data last time. Obviously, you need to enhance the capabilities of database systems from the traditional data types, mostly alphanumeric data, into database systems that can both be capable of representing the rich semantics in the different media types, and also allowing the retrieval mechanisms or the query languages to address and retrieve that rich semantics in different ways. And more recently, we see AI obviously taking a central stage in many of the data-centric applications. It, it's it also opens a lot of the doors of opportunities with the inclusion of multimedia data. A lot of progress in that area has been made, as we discussed also last time. But the technologies around AI, as we also cover in greater detail in this class, as applied to multimedia data, will also be part of any multimedia information systems, especially if you are trying to train your systems and expect their performance to be improved as they deal with more data, which typically is the case. So the storage, retrieval, and management of data in a typical multimedia information systems will involve different media types, and different technologies will be involved, as we just discussed. So the media types will have to be typically in digital format. So this brings us to the question of continuous and discrete media. So continuous media or time-dependent media will have a time or temporal dimension. Video and obviously audio recordings are good examples for this, but discrete time or time-independent media or stationary media will be basically independent of time. Text, graphics, data could be good examples. So things like sensory data may also be continuous or discrete depending on the application. So if you have a sequence, time-based, sensory data that is captured with timestamps, that may be regarded as continuous. But if the data is just an instant data, a time-independent version, then that may be considered discrete type media. We made the distinction between analog and digital media data that is represented using real values at real-time instances or in a more continuous fashion. It's typically referred to as analog. So this can refer to being analog in the temporal or spatial domain also. And a lot of times there's some degree of relativity here. If anybody remembers the times of the film, then before the digital pictures, you would basically capture photos on a film, which was not technically digital or digitized. It wasn't discrete. It was more of a continuous, but even the film in its physical sense actually had a finite resolution. This would often be referred to as the ISO, resolution or quality metric. So those old style films also had different quality levels, which would actually refer to the level of the detail that you could capture in those old film-based cameras. So in reality, even most analog or continuous systems in the spatial dimension and even the temporal dimension are not fully continuous, so they won't have an infinite resolution, in other words. But in relative terms, most analog terms, analog media or analog systems typically refer to continuous and non-finite resolution techniques. So even our eyes actually sample the real world, say in our surroundings around us, and we often don't notice this unless you're trying to view motion at high frequencies, high speed motion. Then you may notice the limit of your visual system in sampling the environment around. but we consider our vision system and audio system, etc., and the real world images, sounds, etc., around us as analog in more relative terms. Obviously, in digital form, media needs to be represented using discrete or finite values. So no matter how high the quality of your TV screen, camera, etc. is, it will have a finite resolution, meaning and a certain number of pixels that can be used to represent one shot, one screen of data. This is true also for digital audio formats. So you are basically using discrete values, whether it's in the form of integers, floating point numbers, or simply quantized numbers at a finite resolution. So sampling media is part of the digitization process. It's not the entirety. So you take a continuous representation of media, whether it's in the time dimension or space dimensions, whether it's audio or image or video data or any other type of data. So you collect a finite number of samples in the time dimension or in one of the space dimensions, X, Y, Z, etc. So you represent the media by a finite set of discrete points this way. So rather than having a continuous image representation, you have a finite number of pixels, each one of which represents one color value for an image, or maybe some audio amplitude value for audio digitization, sampled audio data. So you can simplify this idea on a one-dimensional signal. You see here a continuous signal on top. So in the time dimension, you have continuous values, seemingly infinite resolution. Of course, in practice, this is only a theoretical idea, but sampling gives you a certain number of data samples, data values or measurement values of the same signal. So you can be sampling at intervals of capital T, as this example shows. So as a result, for the entire duration of the signal, you have a finite number of sample points or amplitude values. And in most cases, this is done with a uniform sampling model. So you sample at regular intervals. So those length of those intervals may have to be at a certain value so that you can basically recover the signal from the sampled version. So we're going to discuss this in more detail a little later. What we have from the discussion so far, we have already seen and come across several challenging areas and concepts in the data science applications involving multimedia data. So just want to get started with a few of these discussion points. We're going to see some of these in our discussions today, and some more later in next week or beyond. So also, if you have any contributions, any ideas at any point, especially any questions, if you need to clarify anything, do let me know at any point, and let's also add some interactive discussions to this. So
and this is an area that is constantly changing. One development I've been kind of keeping my eye on is there's a lot of investment now in analog chipsets. and it'll be very interesting when those start coming to market for various AI tasks, how they may impact this area. Because right now it's all based on the digital chipset, but it may be a real explosion in this area once there are, for example, in a computer, both analog and digital chips, where the analog chipsets have been optimized for really directly working with this analog data, like sound and like working with images. So it'll be very interesting to see in the years ahead. The ability to work with this is, I think, increasingly going to become faster, more efficient, and I think the capabilities are just going to get greater and greater.
That's true, and that trend is in line with the trend of including more and more multimedia data in most of these applications. Because when you are capable of directly dealing with data type, different data modalities without having to digitize them. So if you can just handle all the signals as they are, and have your semiconductors basically process them in their original analog format, you get rid of a few problems already. So the overhead of having to digitize them, and then of course converting them back to analog. And also you don't lose the resolution or the quality of your signal. So obviously integrating analog and digital processing itself is a big challenge, but once that's addressed and you can keep your multimedia data in its original analog form, that can actually address one of these challenges that we're listing here, different data modalities. So sampling and digitization is one of those obviously challenges that you're facing here, but it's not just a matter of the processing overhead, but of course the potential loss of data or resolution or detail. So one question that we are facing is, how do you store an analog sound on a digital storage? And that, of course, is one of the main reasons many systems try to digitize analog signals in the first place. But analog signals have actually been stored in the past. Anybody would like to take a shot at this? Obviously, the older legacy storage systems like tape recorders, etc. Vinyl, of course, was one of the earliest media that you could record signals, especially audio signals, in its original analog format. But you can basically mimic the same idea with micro devices or nano devices that can keep the audio or other signals in their non-sampled analog format. So you may have micro or nano, vinyl recorders or the tape recorders or similar technologies that can basically just mimic that. So you can potentially achieve higher resolution. The same can go with the optics in much small micro or nanoscale manners. You can store visual data in non-digitized format. This can, of course, potentially have limited applications. You may be able to do this only for critical data initially, because you will be much more limited in how much you can potentially store, retrieve, etc. But for example, in forensics or music industry, the quality of the data, shorter or smaller amount of data, may actually be more important than the efficiency that you may achieve by digitizing or converting to digital format. So obviously there's some cost performance trade-off and issues that you will have to weigh in this area as well. So the correlation and complexity among different data types, especially for synchronized data or when you're trying to address an important and challenging problem like identifying, for example, objects or persons in your media repository. So the correlation can be an important asset and dimension of the data semantics here, and it will also present some complexity issues that will require the efficiency as well as scalability issues. So if you can handle certain number of objects in your repository, again, how can you generalize this to higher numbers, or if you have the capabilities to deal with certain amounts of data, if you're adding up and just increasing the volume of data, how can you scale up by addressing some of these challenges at the same time? Especially for media types, the temporal dimensions, real-time processing, and QoS issues will also be important. So what the multimedia data area has actually seen a lot of important research projects in the QoS area in the past few years. Obviously, the richness and the complexity of the data, especially in the era of the AI, learning technologies, etc., also presents many opportunities, some of which we have not even seen yet in the industry. So this richness, especially in the context of data science applications, can be utilized by taking different modalities and aggregating the semantics and the correlations among different media types towards more either efficient or sometimes more effective, more smart and more intelligent or artificially intelligent decision-making processes in many cases. So we have one application area that I'd like to get into a little later because we are using some of these techniques for that specific application in an active research project. As an example, case here, but the source of the need for new techniques in this area comes from the fact that the traditional data science techniques may or may not be applicable to multimedia data. In some cases, they will be. In some others, they will not. So you need to convert or transform your data in its raw form, starting with the analog, and even in digitized form, your data is still raw data, your media data. So you need to present your multimedia data in a way that will make it useful and practical for many of the established data science techniques to utilize them. So data annotation, whether manual, automated, or hybrid models are used, will be part of this. So you can take your raw video, for example, for any application that may be in question here, and for the machine learning techniques or any other AI technique to be applicable, you need to convert your raw pixel values into different dimensions of data with reduced dimensions, first of all, for efficiency purposes, and also with the relevant features and feature sets for effectiveness purposes for the data science techniques, or eventually the decision-making processes or automation processes, etc., to be able to utilize your multimedia data sources. So Dr. Pierce points out to an interesting site that provides some explanation about the analog signals, digital conversions, so they can the analog signals can be stored in digital platforms, digital media platforms. So we're going to be looking at different media types and getting a bit deeper into some of the technologies and techniques that may be relevant to them. Text, of course, is the basic data format that is typically part of most multimedia systems. It can be structured or unstructured text. It can be indexed in different ways. The semantics with NLP or other techniques can be can be utilized. So this part of the class we won't get in much detail to that. We cover in other parts of the class, but text is still an important and relevant part of a multimedia system, especially its correlation to the data streams that can often make this a very relevant and useful part of any multimedia information system. For example, if you're capturing video and the transcriptions of the video and their relevance with the timestamp information to the pictorial or visual content or visual stream as part of your video data may be very important. So the text that you can capture from the audio stream or the transcriptions or even the screen text that is displayed as part of your recordings and in correlation with the visual data that you have, it can be a great way to index your data, visual data, and even also supply to the AI, training mechanisms. So you can build a correlation model based on the presence of certain keywords in your maybe speech transcriptions, closed captions, or screen text, and the visual or even the audio tracks. So the AI systems can very easily learn from that correlation between two modalities. So text is just as important as other modalities, and its representation, compression, and indexing, and especially the relevance to other media formats can be important. And its compression can either also be lossy or lossless because the representation is typically much more efficient than other media types. The text is often compressed in a lossless fashion, meaning you want to be able to recover or reproduce your data in its origin form. Lossy compression, where you basically give up part of your data, if you will, is often used for compression of audio or visual content, relying on the fact that you or the human visual or auditory system cannot sense parts of the data anyway, and that this is the case with the JPEG, MPEG, or MP3 or similar compression techniques. Very often, if it's in high quality enough, the difference will not be uh, big enough to perceive by any normal human being. So these are some of the areas related to the image or visual media types. Vision or computer vision often refers to the ability to see, represent, or understand the contents. This could be in a very basic form of representing uh, objects. In more complex situations, maybe referring to the events or descriptions of the images. And if you're dealing with obviously video, these descriptions, semantics can be a little more involved, more complex. But at a very basic level, from a single image, extraction, capturing, analyzing, and representation of imagery features is an important part of the computer vision image processing area. So as we will see in some examples in practice, the images are represented by its color values, intensity values. So at every pixel, you have a single number for grayscale or binary images, or typically 3 color dimensions in a color image. This could be RGB, red, green, blue values, or some other 3-dimensional color format. Resolution, as we mentioned, refers to the number of pixels. The higher this number, obviously, the better the quality. By that, what we mean is by higher quality, what we mean is better representation, better approximation to the real world images or perception of images. So some geometric aspects like this distances, for example, the distance between the eyes for face recognition can be a very critical measurement. Some important geometric measurements may be an important part of the representation of the content. And the color, sometimes in the form of color histograms or color distribution, etc., can be also part of our description and perception of an image. So this can provide a measurable, quantitative way to represent the contents of the image, in addition to things like the representation of objects, their relationships, etc. One important distinction in the visual content area is the images versus graphics. I did mention this. Graphics refers to the machine created, synthesized visual content. And obviously, since you have digital representation already, so you're not sampling your graphics content, but the images, when captured from the real world, can be further processed by image processing techniques, or they can go through some computer vision techniques for description, conceptual descriptions of the scenes, objects, etc. And based on those descriptions, images can be created with computer graphics techniques. So this basically just captures the relationship between the real world that surrounds us, that is the source of the real world imagery, the image representation, and the what we call the scene description, the standardized representation, typically of graphics content in terms of objects, shapes, etc. So if you have a vector graphics description of triangles, other shapes, colors, etc., this would be a scene description. And when you basically render that and could create image or sequences of images, you can basically represent that same data in its final format in the form of an image. This is much like HTML content for web pages versus what the browsers will display. So when you take HTML content along with other components, images, etc., the browser will basically present this in its final format, like in the form of an image, but the page is actually represented as a description of markup language elements, etc. Let me just. So these images can be, of course, can be coming from all kinds of sources. Personal for photography, surveillance for security purposes, captured images from video content like movies, sports content, and so forth. And in a multimedia or multimodal system, these visual data will often be integrated with other data. One of those dimensions, in addition to the text, image, sound, video, etc., could be the sensor data. So let's take a look at that aspect. We talked about the integration of different modalities in different contexts and the potential advantages or benefits that of integrating and utilizing the correlation of different modalities. So this can especially be beneficial when the sources of different modalities are somewhat uncorrelated and unrelated. So so if you're just capturing the audio and you know, the visual content, same time of highly correlated data, there may be little that you can benefit from using those different modalities. There may be little use or advantage of that. But when you are integrating the data collected from different modalities that may not be highly correlated, but still relevant and contributing the same application or same purpose, there could be major advantages. So this is one of the interesting research fields of integrating, for example, sensory data, things that you can collect from IoT type sensors, from Internet of Things, sensor or other types of sensors with visual multimedia data. And this can be done at different levels. For example, in the same environment, you may be collecting sensor data of either motion detections, maybe temperatures, temperature changes, etc. And there may be visual sources of information in the form of cameras or stationary image cameras, so video or image cameras. So if you are for example, capturing certain events, interesting events that may be happening in that environment, or if you're feeding your data into a learning model, uh, using multiple modalities may actually present some major benefits and advantages. So one of some kind of a fusion technique, and we can use different techniques here. We won't get into the specific details. Things like fusion techniques like Bayesian or Dempsey-Sheffer or others can be used to fuse or integrate or utilize at the same time different sources of data, some of which may be visual sensors in the form of cameras. But in many fusion techniques or integration approaches, using the raw data by itself, you may have seen or experienced this in some AI techniques, networks, etc. as well. Using the data in its raw format is typically not very productive, especially if you're dealing with larger amounts of data with a lot of semantics involved. So if you're feeding every single, for example, pixel value in your incoming videos, which will result in obviously, first of all, with gigabytes of data and with a lot of unnecessary, repetitions, etc., redundancy in your data, that would not be very productive, and it usually is not. And some pre-processing or intermediate processing to capture some metadata or feature extraction from your videos or images. It's typically part of that process, and this is true for many multimedia applications. And one of the perhaps key features of or distinctions of multimedia data versus traditional data, which may be actually the case even for the simpler the traditional or sensor data that you may be collecting. So a similar feature extraction or pattern recognition or dimensionality reduction technique, which typically involved in going from the raw sensor data into a set of features that you may be reducing to or capturing or extracting from this raw data. For example, you may be collecting the motion or temperature data from a number of sensor points, and the raw data processing can give you the either sudden changes or some averages, some variation data, or some other statistical measure that may most relevantly capture what you're looking for in fusing this data or information with what you're capturing from your visual sensory and what you produce out of that, the feature set that you're obtaining from your visual sensors. And finally, you need to have obviously an effective fusion or integration mechanism, which will produce a set of outputs, maybe some decision points, either specific decisions or ways to aid you in making certain decisions. For example, in determining where a specific event or a security situation or perhaps some other target concept is detected or not. Okay, let's maybe complete this and get to the discussion point in just a few minutes. So I was just going to give an example of this as part of a research project that we did a number of years ago, just to provide an example of integrating multiple modalities for similar purpose, which is one of the typical situations where you use a multimedia or multimodal information system that combines data or information from multiple sources of information for a common purpose. And another interesting example application, just to mention a couple more, is the idea of using the GIS information, combining GIS source of information with the localized again video recordings of the from the traffic cameras that can capture the road conditions, as well as interestingly the social media data that is time stamped and also location stamped. So you can basically integrate and combine, for example, the visual data that you may get from cameras, traffic cameras, like these examples shows. And since you're relying on social media provided the information with their location and also the temporal dimensions, stamp information, you can integrate several dimensions like this that combines both visual processing and understanding of cameras and the location and source of the data, and also some kind of a reliability metric since this is social media content. So you can basically combine several of these dimensions and determine and come up with a final map of the road condition with a certain degree of relevance and reliability. And this can potentially help you or aid you in, for example, directing the disaster efforts, disaster help efforts by being on a real-time basis aware of the road conditions based on both the social media provided data and also the cameras from both common users, civilian users, as well as the professional equipment. So here you're basically referring to the use or the common or instant use of different sources of information again from both visual content or maybe some kind of a traffic sensor data, social media or user provided data that may have text or even video or audio dimensions in them. And finally, just combining and integrating them for a specific common purpose. So this is just another example of what you call a multimedia or multimodal system. And this is also another active research project that we are currently conducting. So this analyzing images and videos and coming up with some relevant and accurate data from that analysis also has different dimensions here, so we won't get into all the details, but you may have to deal with some quality issues from recordings. For example, your video recordings will be blurred or will be affected by things like raindrops or moving cameras, moving objects, unclear images, etc. But if you can basically resolve some of these issues and utilize the information that you can collect, not from a single source, but multiple dimensions from both social media sites, cameras, sensors, etc. The end result, in most cases, will typically be much more accurate, much more useful, much more relevant than the case of relying on a single modality or dimension. And that is the main point that I would like to make from some of these examples. So going back to the point, maybe we can continue and finalize that discussion. Between analog and digital.
I'm sorry, I didn't mean to interrupt what you are doing, and it doesn't pertain to this.
Okay, and anything that you would like to raise or share, everybody? Okay, so let's just finish this discussion. So the idea here in terms of visual analysis was to basically using video captured from the cameras and based on the analysis of the movements of the objects, in this case, obviously vehicles and cars, coming up with some kind of a road condition estimation, and feed that into the integrated decision-making system or mechanism that will eventually, on a real-time basis, that can tell you what the road conditions are at certain points on your map, and without having to without any delays, which can be critical at the times of disaster response, etc. Automate the process of integrating information from multiple sources and doing this on a more real-time and efficient manner. So this can be at a regional level, can be done more efficiently and more effectively using multiple sources of information. And this is basically one of the common points here in the context of this particular example application. So we are going to get into some of the detailed aspects of image, audio, and video analysis after this further introduction on Tuesday and Thursday, just to provide the context of this. So we would see how maybe we can get into some of these, sampling and analog versus digital points at that point also. Starting with some basic concepts, we'll look at some specifics of how image processing and analysis, as well as the audio and video analysis techniques can be used and are used to integrate them into multimedia or multimodal information or systems, similar to several examples that I brought up and we also discussed on Tuesday and today as well. Any questions, comments? We have, as I mentioned at the beginning of the class today, we are going to post some example projects that you can do as part of this class as an implementation of the ideas that we're discussing in this multimedia part of the class. So these should be posted on our Blackboard page. So you can take a look at those between now and next week's classes. We just wanted to let you know about them. So we're going to have a more detailed discussion about those, and they will be relevant to the techniques and methods that we will be discussing next week with respect to the image processing, image feature extraction, and also the retrieval of multimedia content based on the features that will be discussed. But those projects, you can take a look at them, and you will have an opportunity to complete one of the multimedia-related projects, and we will discuss them in greater detail next week.
And I can give students a heads up. Actually, students will be able, if you go into your Blackboard course shell, you can find these projects right now. Where you'll find them is actually, I posted them under working with images. They're under week 7. And all you have to do is click on the image challenge assignment, and there you will see the 3 different ones. A number of students have actually gotten an early start on the project image processing, but there's 2 others, project retrieval and project cut detection. And again, as Dr. Dactus mentioned, we'll be talking a lot more about image analytics. But for example, I kind of view this, I actually worked on the image processing one myself. And the nice thing is it's kind of like a scavenger hunt, meaning there's a lot of good blogs and samples out there. And you'll be amazed that, once you have a focus, I want to know how I can change a color image to black and white. How many different options you have available to you, whether it's code or whether it's an API, or if it's a Python library that has a functionality that will do it for you. But yeah, just look for the image challenge assignment, and that is under week 7, and you can see the 3 challenges and that Dr. Dactus has given us.
Yes, yeah, please do take a look at those project examples and the questions. You can, of course, contact us at any point, but we can have a kind of a broader discussion on those as we actually discuss some of these techniques on image analysis on Tuesday next week. I wanted to allow for a few minutes at the end for any discussions or question and answers. Do let us know if you have any. But otherwise, I'm finished with my part for today.
Yeah, and I'll just say, for students, because I think I may have gotten this started talking about the research that a lot of companies are doing into the analog chipset. There's some very good articles in this area on what they're hoping to accomplish with the analog chips, and so it's an interesting area. I can't say I'm that expert in it because I'm just kind of like you, just kind of learning about the use of analog chips and how they might make certain operations easier, handling them on an analog chip versus a digital chip. But it is an interesting area to watch, and many of the big chip manufacturers are putting some serious R&D into not only the underlying hardware, but then how do you program these analog chips. So it's very interesting. Dennis was mentioning it's kind of interesting, yes, how we store these mediums, and then how you can process these various mediums.
And he was right, and I think I made a similar point in mentioning that there's actually no true analog system in practice. When we look around us, even the optical systems are limited by the quantities and the physical features of photons, etc. So so the true world has a finite resolution, even in its what we call it in analog format. And being analog or digital can be a bit relative than an absolute distinction. So he makes a valid point here, and it's true for the media representation also. Vinyl or traditional recording or representation schemes, also the old films, still had a finite resolution even in physical media. So that was a valid point as well.
Yeah, it's kind of interesting. This particular article that I posted, it was kind of interesting. They were looking at certain operations where they could actually do the operations with let me say, with a small set of analog transistors versus a large set of digital transistors. So it's very interesting. It'll be. I'm looking forward to seeing as this emerges how this technology gets incorporated, into our computing infrastructure. And like so many things, we may not even notice it from our end. We'll just notice that our libraries and certain processing and functionality just goes faster, because underneath it, the algorithms are making, kind of what's happening between a GPU and CPU. It can kind of decide, which things can be better done on a GPU and what can be better done on a CPU, and it kind of optimizes it for us without us even being aware that it's making these decisions. And just for folks that we just got it, I had the advantage that, since Dr. Dagtus was lecturing, I could kind of keep an eye on any news coming across, but it does look that if you have any Friday classes or any Friday activities, like we usually do our seminar at 11, looks like those will switch to remote. So wow, this was quite a week between President's Day on Monday and then a storm on Tuesday, and icy conditions all through the week. Hopefully Monday we will be back to normal.
I was hoping the same for tomorrow, but looks like we'll have another remote day.
Yes, and I will get the word out to folks that yes, we will do as much as we can. We'll just do it remotely.
Okay, thank you for letting us know.
All right. Well, everyone.
Dr. Liz?
Yes.
I have a question, just personal question. So if you can stop the recording.
Sure. Let me wrap up the recording and then I'll stick around if there's any additional questions.